All right, here we go. Today, as we start Newton's three laws and we look at balanced and unbalanced forces, I am going to start with Newton's first law. This is the one that I feel like, Abby, we should be the absolute most familiar with, because if you remember the definition of inertia, and I know that you did because in the game that we played just before this, you kept answering the definition of inertia for the definition of Newton's first law. I'm going to be honest with you. That's the same thing. There will not be, at least on the test that I give you, a definition that's supposed to be Newton's first law and one that's supposed to be inertia, because they're the same thing. Otherwise, it wouldn't be called the law of inertia. So when we get into Newton's first law as the law of inertia, like all we have to remember for Newton's first law is, we're not doing that right now, is what Newton's law is. So let's put our notes in for this. I will pause. So just for my folks that are at home or online or whatever, Newton's first law is the law of inertia. An object at rest will stay at rest until something moves it, just like the Gatorade bottle, which somebody has moved. And an object in motion stays in motion until something stops it, but obviously it has been stopped because it's not still moving. So that's something we can think about. So Newton's first law, I'm not going to spend a ton of time on that one because I think that one is fairly simple to understand. Close the whiteboard, and now we will talk about Newton's second law. Again, we've kind of gone over this. If you remember, when we talked about either the toy train or the regular size train, or playing that game at recess, Harrison, where we had the small rock rolling down the hill versus the giant boulder, Newton's second law. The greater the mass of an object that's being moved, the more force you need to move it. And I think that everyone in here really does kind of understand this already. You may not have the exact words for it, but you kind of understand it. Again, if I said, I need somebody to take this chair into Ms. Tulloch's room, one of you would raise your hand and you would take the chair into Ms. Tulloch's room. If I said, I need you to move that bookcase, like, I don't think just one person, right? Easton raises his hand, says, I'll do it. Like, somebody else is going to raise their hand, be like, can I help him? Because you would be like, there's no way any one of us is going to pick up that whole bookcase over there and take that into Miss Tulloch's room. It has too much mass. We can't pick that up. So you kind of already have the understanding of this. The more mass something has, the more force you're going to need to move it, and you're going to need the same amount like of force to stop it, right? Just as I would be able to stick my foot out and stop that little train from moving from our previous notes, I'm not going to be able to stick my foot out and stop a real train from rolling down the track. Right, it's just going to run right over my foot and keep on rolling because it takes more force to stop something with more mass. So that one I think is kind of easy to understand too as we go through Newton's second law. We'll open this up. So just to repeat for my folks that are at home taking notes, we're taking notes right here on Newton's second law. The more mass an object has, the more force it will take to move it and to stop it. For example, we said it takes a little bit of force, not a lot of force, to move and stop a toy train because it has very little mass. The opposite for a real train, because that train has a lot of mass. It does take a lot of force to move and to stop it. All right, so we've got Newton's first and second law done. Probably going to end up skipping this for now. I'll come back and watch this with you in just a few moments. This is a pretty cool video, and I like this video a whole lot, but we'll watch that. I can't play that. Copyright stuff, and we'll do that later too. Newton's third law. Newton's third law is that for every action there is an equal and opposite reaction. For every action there is an equal and opposite reaction. So if I am going down the hall today and there's a little kindergartner that runs around the corner and bumps into me, which has happened before, let me be very honest with you, they kind of like bounce off of me and fall on the floor and they start crying. Because they do not have a lot of mass, they do not have a lot of force, they are not going to move me. However, if I was going down the hall and that same NFL lineman we were talking about pushing back and forth earlier was running down the hall as fast as he could, and I came around the corner, who? Sure, I don't care who it is. And I come around the corner and they hit me, I am going to go flying. Because that would be the equal reaction. You have more mass and more force, it's going to push me a lot further. We've said it once in here, if not 100 times. If I just drop the bouncy ball, no one in here expects the bouncy ball to hit the ceiling because I didn't add a lot of force. That would not be an equal reaction. However, if we slam the ball down as hard as we can, we would not be shocked if it hit the ceiling. So again, for every action, there's an equal and opposite reaction. Just to repeat for my folks at home and so you can listen while you're taking the notes. Newton's third law: for every action, there's an equal and opposite reaction. Here's our example. If a small kid runs and bumps into you, you would barely move. If a huge NFL lineman ran into you, you would get knocked backwards pretty far. All right, I want to go over some examples of Newton's third law, some things that we might see later on. If you've ever been able to shoot a gun before, you know that there is a kickback that happens when you shoot a gun. Whether you're holding a pistol, whether you're holding a pistol or a shotgun, it doesn't matter. It definitely kicks back, and that is the opposite reaction. And I'll be honest with you, like shooting like a .22, which is a pretty small bullet, there is not much of a recoil. However, when you put a shotgun, like a 12-gauge shotgun there, and you shoot it, it does recoil massively. Shooting off a rocket. Again, we've seen the videos of that. And when we shoot off a rocket, you can see the equal and opposite reaction. You see the flames coming out of the backside of the rocket. You can see like the trees and the animals and the air and the water around that moving a lot because there's a lot of force being expelled. And then the opposite reaction is that the rocket is able to overcome Earth's gravity and move. I would not recommend doing this because you could definitely get hurt unless the boat is rather large. When you jump into a boat that is sitting on the water, the boat is going to go down just a little bit as a reaction to you jumping in. Obviously, the bigger the person, the more the reaction would be. When you hit a nail, you're hammering in nails, that is an equal and opposite reaction. The reaction is as you hit it, it gets driven into the wall or the wood or whatever, and the hammer does bounce back up a little bit, so don't put your face too close to that. That one's okay. I mean, I know when we watch the video, I think there's a little bit better example of them sitting in a boat. I like the example that they had of the bumper cars. Like, the bumper cars do go different speeds. If you're barely moving and you hit somebody, you barely bump. But if you do get that chance to, like, floor it and go all the way across it and run into your friend, you both bounce back pretty far. It's a lot of fun. So, again, equal and opposite reactions. Just some examples there of things that we might see, and probably another video. I'm going to pause. All right. With all those wonderful technical difficulties, we got to figure out what's going on maybe during recess. Let's go over this. This is not the one that I wanted to use, but this one will work just fine. So we're going to talk about balanced and unbalanced forces. You should know that a force is a push or a pull. That's not very difficult to understand. Now, we know that force is measured in newtons, right? So you're not going to have to do any of this math that I know of unless I start to see this pop up. It is, however, really easy, Aubrey. Like when you're measuring in newtons, like if there's like a box and it needs 500 newtons to move it, and you push on the box with 400 newtons of force, the box won't move. If you push on it with 501, the box will start to move. And if you push it with like 3,000, it's going to move very quickly. Not super difficult to understand. But again, to make this car move, the person pushes with a force of 5,000 newtons, or they get in the front of it and they pull it with 5,000 newtons. Either way, it takes 5,000 newtons to move that car. This arrow shows you how much force is going on. It's possible that you might see that later on. It just kind of gives you an idea of how much force is being applied to this object. And they can't just give you an object and say, well, the object moved. They got to tell you what force it takes to move that object. So again, I'm not going to do that one. Now, I've got two people pulling here, but I've got this lady over here pulling with 500 newtons of force and this lady over here pulling with 100 newtons of force. Which way do you think this rope is going to move? To the right or to the left? Olivia? It's going to move to the left because this lady over here is pulling with more force. Again, this force, you know that this arrow is a little bit longer, if you notice that or not, but that means it actually has more force being put on it, which is kind of fine. We're not going to label that at all. Balanced and unbalanced forces. We're going to get these notes jotted down, and then we're going to hopefully be able to review very quickly as we move on. Balanced forces. Again, Lindley, when you see the word balanced, just think of somebody sitting on a seesaw. There's one person on this side and one person on this side, and the seesaw is balanced. Is it moving? No, because it's balanced. It's sitting there. If you put more weight on one side, it becomes unbalanced. Would the seesaw move then, Easton? If I put more weight on one side and it's unbalanced, it's going to move in the direction of the unbalanced force. So again, balanced forces is equal. It does not change an object's motion. It means that there is not movement. Unbalanced forces means that the forces are not equal, and you're going to see movement in that object. I'm not going to do that. Again, outside playing tug of war, you have this side versus this side, and they're both pulling with the exact same force. There is no movement at all, Cora. If you look at the one under that, though, you can see that this side on the right is not pulling as hard as this side on the left, so yet again, the side on the left is going to win. So just to review for my folks at home while you are also listening and taking notes, balanced forces. Remember, you've got opposite forces forces in opposite directions that are equal. So you've got one side of the rope pulling with 500 newtons and the other side of the rope pulling with 500 newtons. Hudson, there is no movement when the forces in opposite directions are equal. However, if you have one side pulling with 1,000 newtons and the opposite side is pulling with 500 newtons, it is going to move, and it's going to move in the direction of the greater force. So balanced, just like that seesaw, if both sides are the same, there is no movement. And unbalanced, if you have an unbalanced seesaw, that seesaw is going to move in the direction of the greater force.